Good evening. I really think I must begin again with Halley's Comet. We can still see it from here, even though it's now starting to set inconveniently soon after the sun. The weather's been pretty terrible. From my own observatory, I haven't been able to take nearly as many photographs of it as I wanted to. But here's a rather lovely picture from Australia, from the Siding Spring Observatory. And there we see the comet, and we see its tail quite nicely displayed. And somewhere inside the comet's coma is that mysterious icy nucleus. Of course, the camera was following the comet, and therefore the stars are drawn out into short trails. There's also been a very interesting series of observations, extending over about 12 minutes, from Tenerife. And I do mean Tenerife, not La Palma this time. And this happened when the comet passed in front of and occulted a star. There's the comet in the middle of the screen, and it appears to be dancing about, not because it really is. This, of course, is an electronic picture. And there, over to the right-hand side, you can see the star. Now, as the comet approached the star, the occultation drew near. Now the star's light is coming to us through the comet's coma. And you can see that the star's light doesn't appear to be dimmed, because the coma is made up of such very tenuous gas. And now, at closest approach, it looks almost like a double coma. But of course it's not. The upper one is the star, and the light still isn't dimmed very much. And bearing in mind that the comet's coma is now comparable in size with the sun, that shows you how incredibly tenuous the cometary material is. Every time Halley's Comet comes round, the crazy gang are in full cry. And the comet gets blamed for political revolutions and upheavals and storms and cyclones, almost everything. That, of course, is absolute nonsense. The comet can't possibly affect anything. But we do depend entirely upon our own particular star, the sun. And it's the sun I want to talk about now. I realize our program is called The Sky at Night, and the sun's a daytime object, but after all, it is a star. And by learning more about the sun, we're also learning more about the other stars. And we depend upon it entirely. For example, consider the seasons. And these are due to the tilt of the Earth's axis. In our winter, as now, the North Pole is tilted away from the sun, and the sun's rays are striking us obliquely, and we have our winter. Then we come on to the spring equinox, and that's when the sun reaches the equator of the sky, passing from south to north. That's what we call the Tropic of Cancer, and then day and night are equal everywhere. Then in our summer, the North Pole is turned toward the sun, and we receive the full benefit of the sun's rays, even though in the summer solstice we are actually a bit further away than we are in winter, about 94.5 million miles as against 91.5 million. Then we come back to the autumnal equinox, when again the sun reaches the equator, this time passing from north to south, and that heralds our own winter. Well, that's been known for a long time. We also know the sun's very hot. But not everybody believed so, and even Sir William Herschel, the great observer who discovered the planet Uranus, that's now so very much in the news, even Herschel believed that below the bright surface of the sun there was a cool, temperate region where people might live. And there's a lovely old woodcut of that kind of idea. Not, I think, very likely. The sun is indeed a very hot globe. And even at the bright surface, the surface we can see, which we call the photosphere, the temperature is something like 6,000 degrees centigrade. And as you go in, the temperature rises very quickly, until at the sun's core, the temperature is at least 14 million degrees, and it may be rather more than that. And that is where the sun's energy is being produced. But just how does the sun shine? Well, to start with, it's not burning. For one thing, it's much too hot to burn. It's depending on what we call nuclear reactions. And the essential fuel is hydrogen, which is the lightest element in the universe and also much the most plentiful. And the sun contains a great deal of hydrogen. So let's see what happens. What happens basically is that hydrogen builds up into the next lightest element, which is called helium, but by a rather roundabout kind of process. Here we have a hydrogen nucleus, which we call a proton, that's colored in red. And the first step in this cycle is that another proton comes along and meets it, and we have a neutron, which is in blue, with the emission of a positron, lower right, and also a neutrino, upper right. And we have now a nucleus of deuterium, which is heavy hydrogen, made up of one proton with a positive charge and one neutron that has no charge at all. The next thing that happens in the cycle is the arrival of another proton, which joins the deuterium. This time we have a photon emitted, and we now have a nucleus of helium-3, 2 protons, 1 neutron. And then this meets another helium-3 nucleus, and this time we have a neutron, we have a proton emitted, another proton emitted, and we finish up with a nucleus of helium-4. And you can see what's happened. The helium-4 has been built up, And every time that happens, a little energy is set free and a little mass is lost. And it's that energy that keeps the sun radiating, and the mass loss amounts to 4 million tons every second. But please don't worry, there's plenty left, and we'll come to that later on. Now, the bright surface of the sun is called the photosphere, and it's not uniform, at least not always. On it, we can sometimes see dark patches which are known as sunspots. And that drawing of the sun was made some years ago when the sun was more active than it is now. You can see a large spot there with a central dark portion and a lighter surrounding area outside it. But that was made when the sun was active, and to some extent the sun is a variable star. Every 11 years or so, it's very active, plenty of activity there, flares, many spots. And then activity dies down until there may be periods, as now, when the sun shows no spots at all for quite a number of consecutive days. And that's been happening quite recently, and I know this because I do take daily records myself. There's a solar cycle with peaks every 11 years or so. Not absolutely regular, and for some time it was suspended. We'll come back to that later. But in our time, there had been regular troughs and peaks. And every 11 years, we get good activity. Not always equal, I may say. A very high one in 1958. But the last maximum occurred round about 1980. And now, in 1985-86, we are at the minimum of the cycle. And spots are comparatively uncommon. And there's a photograph taken by Douglas Arnold a few weeks ago. And that shows the only sizable spot that has been on the disk in some time now. And it's going to be some years yet before the sun's activity builds up again. But of course, one can study these spots telescopically, and for that purpose, I use my 5-inch refractor. But I'm going to give you yet again the warning I've given so many times, because believe me, it is important. Never look at the sun directly through any telescope or any pair of binoculars. You will simply focus all the sun's light and heat onto your eye, and you'll blind yourself permanently. And believe me, this has happened, so never do it under any circumstances. And recently, I was quite shattered to have a telescope catalogue advertising a small refractor, and it also advertised this. And that is a solar filter. And it was said you could put this on the eyepiece of your telescope and then look at the sun direct. And it's a most dangerous thing to do. Because for one thing, it may look dark. If not dark enough, it won't give your eye full protection. And in any case, it's always liable to splinter without warning. So under no circumstances do that. If you want to use a telescope to study sunspots, there is only one sensible way to do it, and that is by projection, as I am doing here with my 5-inch refractor. You can see I am using the telescope as a projector, and on the screen there you can see the sun's image. And if there had been any sunspots, which at that stage there weren't, they would have shown up very well. But please remember, never, under any circumstances, look direct, even when the sun is very low down and looks very harmless. But the 11-year cycle is not entirely regular. We never quite know what's going to happen. And it may not be a permanent feature. And there's a curious episode called the Maunder Minimum, so named because it was described by old records by the British astronomer E.W. Maunder a long time ago now. And it looks as though between about 1645 and 1715, there were almost no sunspots at all. The solar cycle was suspended. And that had all kinds of effects. In particular, it affected the shape of the sun's corona, which is the sun's outer atmosphere, a lovely pearly mist made up of very thin gas at a very high temperature, which you can't normally see without special instruments, except at the time of a total solar eclipse. And eclipses occur when the moon goes in front of the sun and temporarily hides it, and they're the three kinds: total, partial, and annular. And the total eclipse is much the most interesting of these. The moon goes round the earth goes round the sun, and so there must be times when the three bodies line up. And here we have that situation. There's the moon in the middle of the picture, and from that you can see the cone of shadow caused by the sun's light coming from the upper right and upper left of the picture, and that cone just touches the earth. And that's known as the umbra. And if you're standing in that area covered by the umbra, the moon will entirely blot out the sun. And the grey area to either side of the umbra is called a penumbra, and that's an area of partial shadow where not all the sun is covered. But if you can see a total eclipse, it really is a magnificent sight. And that's a photograph of an eclipse I saw a few years ago from Java. Although from England, I'm afraid, you've got to wait until 1999. They are visible in other parts of the world. If the umbra misses the Earth, then you don't get a total eclipse, you get a partial eclipse. And that's interesting to watch, but not nearly so important, because you can't see either the corona or the prominences. But there's a third kind of eclipse. The moon's path around the Earth isn't quite circular. And if exact alignment occurs when the moon is furthest away from us, it appears slightly smaller than the sun, the umbra doesn't touch the Earth, and what happens is you get the dark body of the moon surrounded by a ring of sunlight. And that was an annular eclipse I photographed a long time ago now from the Greek islands. Again, interesting, but you can't see the corona and you can't see the prominences. But the shape of the corona is affected by the state of the sunspot cycle. Now let's go back to the Maunder minimum between 1645 and 1715. Obviously, no photographs, not many drawings, but it does look very much as though the corona was not nearly so much in evidence as it normally is. And that impression may show what an eclipse may have looked like in that period, although, of course, we can't be certain. But the sun has other effects, too. Slight variations in the sun certainly affect our climates, and there have been times when frost fairs were held on the Thames, although we haven't had any of those for a long, long time now. And then, what about aurorae or polar lights? Now, those lovely glows in the sky are due to electrified particles sent out from the sun, which cross the 93 million mile gap and cascade down into the Earth's upper air and produce those displays. They are magnetic, therefore they go toward the magnetic poles. We don't see very many aurorae from South England. You see plenty from Scotland. And, of course, aurorae are commonest when the sun is active. And it does appear that during the Maunder minimum, 1645, 1715, almost no aurorae were seen at all. And the great astronomer Edmund Halley never saw an aurora until the end of the Maunder minimum, even though he'd spent many years in trying. Again, we can't be certain about that, but the records do seem reasonably complete. And so there's a great deal about the sun that still puzzles us. And also, there is what we call the neutrino problem. I mentioned neutrinos just now when talking about the production of solar energy. They are particles with no mass, or virtually none, and no electrical charge, so they are very difficult to detect. And one way to do that is to make them interact with atoms of chlorine when they produce radioactive argon that you can track down. And chlorine is contained in cleaning fluid, and there's a most remarkable underground solar observatory near Deadwood Gulch in South Dakota, where we went with the Sky at Night some years ago. And there's a huge tank of cleaning fluid in which the experimenters are trying to trap solar neutrinos. And they're only finding about 1/4 as many neutrinos as they expected to do. So something is wrong, either with the theory or even possibly with the sun. It's been suggested that the sun may even have switched off for a bit. Well, that doesn't seem very likely, frankly, but it could be, I suppose. And also it's been supposed that there may be slight variations in the sun's size. It's vibrating, it may be temporarily shrinking. Again, we don't know. And really, there is a great deal about the sun that still puzzles us, even though we have found out so much. But what we can do is to look backwards and forwards in time and just see how the sun has evolved and what's likely to happen to it in the future. Now, the sun began by condensing out of a nebula, a cloud of gas and dust in space, more than 5,000 million years ago. A ring of material formed round the shrinking sun, and gradually the planets built up out of that material by the process we know as accretion. It took a long time, of course, but the final result was the solar system we know today, with the sun in the middle and the planets orbiting it at different distances. And the age of the Earth we know to be something like 4.6 thousand million years. Now, the sun itself goes round the center of the galaxy, and it takes a period of about 225 million years to do so, and that's sometimes known as the cosmic year. So let's look forward now and see what's liable to happen to the sun in the future. Well, as we saw, the production of energy is due to helium being built up from hydrogen. But there are fewer helium nuclei than there were original hydrogen nuclei, and therefore there's got to be some kind of compensation if the sun's going to stay stable. And the only way to do it is for the interior temperature to heat up, the core temperature. And although we believe the core temperature is about 14 million degrees, which will explain the neutrino problem, it could be a bit more than that. But certainly it will increase, and in something like 1,500 million years from now, the sun will be 15% more luminous than it is today. And that means that the climate of what is now Arctic Canada will be very much the same as the modern California. But things will go on, and in 2,000 million years from now, the sun will be twice as luminous as it is today. That means that the Earth's temperature will have risen by about 100 degrees, and the oceans will start to boil, and very unfortunate for life, I think. And then, over the next 250 million years, the sun will turn into a red giant star, with a diameter of something like 80 million miles, and a luminosity several hundred times what it is at the present moment. And that may well destroy the Earth. And even if not, the Earth's surface will turn into a sea of molten lava, and certainly the sun would fill almost the daytime sky. And even if the Earth survives, which I think is doubtful, then life here certainly won't. But that's not the end of it. The sun will then blow away its outer layers altogether, turning temporarily into what we call a planetary nebula. And there are plenty of these planetary nebulae around. And then what's left of the sun will collapse into a very small, super-dense star of the kind known as a white dwarf. And that may happen something like 75 cosmic years from now. And the sun will then go on shining very feebly for a long, long time, until at last all its light and heat leaves it, and it turns into a cold, dead black dwarf. So that's the picture, and life on Earth certainly hasn't got a limitless future. But I don't think it's very depressing, because there's a long, long time ahead yet, and in any case, if mankind survives for that long, I have no doubt we'll be able to find some kind of solution. Now, at the moment, the sun is sending out electrified particles in all directions, making up what we call the solar wind. And that has an interesting effect upon comet tails. As the comet comes into the sun, the solar wind drives the gas particles out, away from the nucleus, and so as the comet passes perihelion, or closest point to the sun, the tail swings round, and subsequently it actually goes tail first, as Halley's Comet will do after its perihelion on February the 9th. But you know, there are problems about the solar wind as well. In particular, we don't know much about the solar wind as it occurs over the sun's poles, but we may find out quite soon with a very interesting probe called Ulysses. And that's due to be launched in May this year from the Space Shuttle, and that'll be looped round the planet Jupiter after about 100 days, and then it will come in and pass over the sun's north pole in early 1990 and tell us about conditions there. And that should give us much additional information about the solar wind. But also, the Voyager 2 probe has been sending back information about the solar wind as well. That, as you know, is now on its way to Uranus, having bypassed Jupiter and Saturn. We'd thought that by the time the solar wind reached Uranus, it would slow down. But apparently, that is not so, as the Voyagers have told us. And that's another thing we hadn't expected at all. But of course, all the emphasis is now on the Voyager 2, because the Uranus encounter is very close ahead. It occurs on January the 24th. We've already had pictures. This was the very first picture of Uranus sent back from Voyager 2 last July, and it doesn't show very much. And here is the latest picture we have in November, and that again doesn't show very much. In fact, Uranus appears to be an almost featureless planet. There are no weather systems there that we can see. And this is very interesting indeed. What are we going to find when the probe makes its pass? And what about those satellites, of which there are 5? And what about the strange dark rings? Uranus is a very mysterious kind of place. Obviously, we're going to be able to bring you news. We'll be over at the Jet Propulsion Laboratory in Pasadena, California, for the Uranus pass. And on our February program, we'll be able to tell you just what Voyager 2 has shown us. Meanwhile, our newsletter's ready. If you want it, then as usual, send a stamped addressed envelope to newsletter number 20, The Sky at Night, BBC Television, London W12 8QT, and we'll send you your newsletter. And our next program is going to be on February the 4th, when we'll bring you all the news right out from as far as Uranus. Good night.